Imagine a simple world, a grid, and somewhere inside it, an agent. The agent doesn't know anything about this world yet. It doesn't have a map, it doesn't have instructions. All it knows is that somewhere out there there's a goal, something valuable. So it starts moving, trying things, going right, going up, sometimes going the wrong way. It's exploring, learning through trial and error, and when it finally reaches the goal, it gets a reward, plus 10. That's the basic idea behind reinforcement learning. An agent explores an environment, takes actions, and learns from the rewards it receives. Let's look at this more carefully. We have an agent, and we have an environment, and there are rewards. The agent takes an action in the environment. The environment responds with a reward. And it also tells the agent what state it's in now. This cycle repeats over and over. Observe, act, receive a reward, improve. That's the reinforcement learning loop. Here's our environment again, a 5 by 5 grid. And here's the agent, sitting in one of the cells. The cell the agent is in right now, that's called its state. It describes the agent's current situation. Every time the agent moves to a new cell, it enters a new state. S1, S2, S3, S4, S5, each one is a different situation. The collection of all possible states is called the state space. So remember, a state is simply the agent's current situation. The agent is in a state. Now it needs to decide what to do. It has choices. It can go up, down, left, or right. These choices are called actions. Each action is labeled A1, A2, A3, A4. In this grid, the actions correspond to directions. The agent picks one, say, go right, and it moves. In reinforcement learning, we write this as, in state S, the agent takes action A. An action is simply a decision the agent makes. Every action produces a consequence, and that consequence comes in the form of a reward. Here's our agent. There's a goal worth plus 10 and a danger zone worth minus 5. When the agent reaches the goal, it earns a positive reward, plus 10. But when it hits the danger zone, it gets a negative reward, minus 5. Rewards are feedback. They tell the agent whether its actions were helpful or harmful. Let's compare two agents. On the left, the agent hasn't learned anything yet. It moves randomly, bouncing around the grid without direction. On the right, the agent has learned from experience. It moves directly to the goal and earns the reward. The difference? Learning. Through repeated experience, the agent figures out which actions lead to better outcomes. After enough experience, something interesting happens. A pattern emerges. In every cell, the agent now knows which direction to go. These arrows represent the agent's strategy. The agent follows this strategy and reaches the goal efficiently. Over time, good actions become more likely. A consistent strategy takes shape. This is the result of learning. This strategy, this set of rules for choosing actions, has a name. It's called a policy. In mathematical notation, we write it as pi of a given S. It tells us, given a state S, which action A should the agent take. The policy is the agent's playbook. Follow the policy, reach the goal. A policy is simply a rule for choosing actions. There are different kinds of policies. Let's start with the simplest one. In a deterministic policy, each state has exactly one action. No randomness, no uncertainty. The agent always does the same thing in the same situation. Follow the arrows, reach the goal, every single time. Deterministic policy, one action per state. But sometimes the agent doesn't always pick the same action. Instead, it assigns probabilities. Go right with 60% chance, go up with 30%, go left with 10%. This time it went right, but next time it might choose differently. The notation pi of a given S now represents a probability distribution over actions. A stochastic policy means the agent chooses actions with probabilities. The agent's goal is simple: get the most reward possible. Here are two options. Path A gets plus 5. Path B gets plus 10. Which would you choose? The agent should choose the path with higher reward. And that's exactly what a good agent does. Reinforcement learning is about choosing actions that maximize reward. But in most problems, rewards don't come all at once. They accumulate over time. As the agent moves through the grid, it picks up rewards along the way. Plus 2, another plus 2, and plus 6 at the goal. Total reward, 10. The total reward is the sum of all rewards collected over time. Here's an important idea. Sometimes the best action doesn't give you an immediate reward. There's a small reward right next to the agent, plus 3, easy to grab. But farther away, there's a much bigger reward, plus 10. A smart agent looks ahead. It gives up the small reward now to get the bigger reward later. Good decisions consider future rewards, not just what's right in front of you. Not all states are created equal. State A is far from the goal, not great. State B is closer, better. State C is right next to the goal, much better. States closer to the reward are more valuable. Some states lead to better future rewards than others. Can we put a number on how good a state is? Yes, we call it V of S, the value function. Every cell now has a value. Low numbers far from the goal, high numbers close to it. This cell has low value, this one has high value. V of S measures how good a state is. Let's visualize the value function as a heat map. Cool colors like blue mean low value. Warm colors like red mean high value. You can see the gradient. Value increases as you get closer to the goal. Higher value states lead to better outcomes. V of S gives us a complete picture of every state's worth. Now here's the key insight. If we know the value of every state, the agent can just follow the gradient. At each step, the agent looks at its neighbors. Which one has the highest value? It moves there. Then looks again. Highest value? Move there. By always stepping toward higher value, the agent naturally reaches the goal. Agents move toward higher value states. So if we have the value function, we can build a policy from it. The agent looks at each neighbor's value. 7, 9, 5, 4, 9 is the highest. So the policy says, go right. This is how value functions and policies connect. The value tells you where to go. The policy is the rule that follows. The policy simply chooses actions that lead to higher value states. We said future rewards matter. And they do. But there's a catch. A reward that's 2 steps away feels more certain than one that's 10 steps away. So we discount future rewards slightly. Not because they don't matter, but because closer rewards are more reliable. Sometimes the agent prefers a slightly smaller reward that's more certain. Reinforcement learning balances immediate and future rewards. Let's make this concrete. Imagine getting plus 10 at different points in time. We introduce a discount factor, gamma, set to 0.9. The same reward of 10 becomes 9 after one step, 8.1 after 2 steps, 7.29 after 3. The further in the future, the less a reward contributes to the total. This is the discounted return, the total value of all future rewards, each one discounted by gamma. So what does V of S actually mean? From any state, there are many possible futures. Path A, Path B, Path C. Each one collects different rewards. V of S is the average of all these possible returns, the expected return. V of S tells you, on average, how much future reward can you expect starting from this state. We've been talking about the value of states, but what about the value of actions? From this state, each action has a different value. Going up is worth 8, going right is worth 12, going left is worth 5. The right action has the highest value. Q of S, A tells us, how good is it to take action A in state S? The policy picks the action with the highest Q value. If we know the Q values for all actions, then the value of the state is simply the value of the best action. V of S equals 12, the maximum Q value. The value of a state comes from its best available action. Now for one of the most important ideas in reinforcement learning. The goal has a value of 10. Right next to it is state S. Moving from S to the goal gives a reward of plus 1. What is the value of state S? The goal is worth 10, but we discount it. Gamma is 0.9, so 10 becomes 9. Add the reward of 1, and we get V of S equals 10. The value of a state equals the reward you get now plus the discounted value of the next state. This one idea is the foundation of almost every reinforcement learning algorithm. To compute the optimal value of a state, we evaluate every possible action. Up gives 8.2, right gives 11, left gives 5.4. The optimal value is the maximum, 11. The Bellman Optimality equation says, take the best action, and that gives you the true value of the state. So how do we actually compute these values? We start with all values at 0, except the goal, that's 10. Now we update the cell next to the goal. 0 plus 0.9 times 10 equals 9. Then we update the next cells and the next. Values spread outward like ripples from the goal. After many iterations, every cell has a value. This process is called value iteration. Repeatedly update, repeatedly improve until the values converge. There's another approach called policy iteration. Start with a random policy, arrows pointing in arbitrary directions. Step 1. Evaluate the policy. Figure out how good each state is under the current set of arrows. Step 2. Improve the policy. Update each arrow to point toward the highest value neighbor, then repeat, evaluate again, improve again. After just a few iterations, the policy converges. Policy iteration alternates between evaluating and improving the policy. Everything we've seen so far assumed we know how the environment works. But what if we don't? At the start, the agent has no idea which actions are good. But as it moves and receives rewards, it starts to form estimates. With every experience, the estimates get a little better. Eventually, the agent learns which actions lead to better outcomes. Agents learn action values by interacting with the environment. There's a fundamental tension in reinforcement learning. The agent knows a path that works. Following it is exploitation. But there might be a better path it hasn't tried yet. So sometimes the agent needs to explore, try random actions, wander into unknown territory. Sometimes exploration discovers better strategies. The key is balance. Mostly exploit what you know, but occasionally explore something new. Reinforcement learning balances exploration and exploitation. Learning takes time. In early episodes, the agent behaves randomly. Later, it discovers shorter and more efficient paths. Eventually, its behavior becomes consistent and effective. Reinforcement learning improves through repeated experience. Let's put it all together. We have an agent and an environment. The agent takes an action. The environment returns a reward and the next state. The agent updates its values and its policy. Then the process repeats. Through this continuous cycle of acting, observing, and learning, the agent gradually discovers better strategies. That is the reinforcement learning loop. What you've just seen is the core idea behind reinforcement learning. An agent interacts with an environment, receives rewards, and gradually improves its decisions through experience. From simple grid worlds to complex, real world problems, this same learning loop powers many modern AI systems. But this raises an important question. How does an agent actually learn those values and policies from experience? In the next video, we'll explore one of the most important algorithms in reinforcement learning, Q learning.